Hello, Professor. Today I'm here to talk about my research topic this year. The title is 100 gigabit per second PON downstream using direct detection and linear environment equalization. Here is the outline of my presentation. I'm now working in the optical access and in a specific architecture, passive optical networks. The 25 giga and 50 giga PON are now in advanced standardization, so that 100 giga PON is today a very hot research topic. The higher bitrate PON, like 150 giga and 100 giga PON, must face the following main issues. The first one is a limited available bandwidth, and the second one is chromatic dispersion. To deal with the limited bandwidth, we performed digital signal processing to use higher order modulation formats and reuse the existing 25 giga optoelectronic, and also in combination with the adaptive equalizer. As for the chromatic dispersion, the CD digital pre-compensation can be used to pre-compensate the link accumulated dispersion only at the transmitter side. Here is the architecture of CD-DPC technique. The link length L is now in advance, so we can emulate the accumulated dispersion at the receiver side with only an opposite sign, that is, minus D multiplied by L, to compensate the chromatic dispersion. This technique is based on the file filter and a dual-arm IQ-Mach-Zehnder modulator. Here are the simulation setups. We performed 100 gigabit per second with 3 modulation formats, PAM4, PAM8, and partial response PAM4, and also 2 types of receivers, SOIA plus PIN and APD, with both 25 giga and 50 giga optoelectronic. In the receiver DSP, FFE and DFE plus FFE are used. We proposed two structures. The first one is IMDD. We performed analysis both in the back-to-back case and also a 20 km single-mode fiber. For CD-DPC-DD architecture, the additional complexity will only be added at the optical line terminal side. Finally, here are some obtained simulation results, but we also obtained experimental confirmation in the lab. On the left is accumulated dispersion versus required received optical power. By using 25 giga optoelectronics, SOIA plus PIN with IMDD architecture in O-band. From the figure, it's symmetric with respect to the deeper L equal to 0 value. And we can also see that for the partial response PAM4 with FFE, the deeper L range from -80 to 100 picosecond per nanometer can be covered. On the right, it's a link length L versus achievable optical path loss by using also 25 giga optoelectronic SOIA plus PIN with DFE but in the C-band. By applying CD-DPC, the optical path loss equal to 29 dB can be achieved by using PAM4 in a from 7 to 12 km range and from 7 to 14 km range for partial response PAM4. At last is the future work. We could perform some square root technology in the receiver DSP and also a new type of receiver SOIA plus APD. Thank you for your time.